Okay, so this lesson is on equations that are quadratic in form. There is a homework assignment on equations that are quadratic in form, so this is perfect to watch before you do that homework assignment so that you have an idea of what you need to do and you can get some help on like recognizing when you need to use this technique or not. So first, what does quadratic in form even mean? You have to understand what this means in order to know when to use the technique. So quadratic equations, we have ax squared plus bx plus c. That's supposed to say equals 0, not c, although it could equal any number, I suppose. But hey, that should be a 0. And quadratic in form means that you can rewrite it to look like that, but you do a substitution. And we usually do a substitution with the letter U. I don't know why U was chosen when we do substitutions, but we use the letter U for substitutions in math for tons of things. Even in calculus, we use the letter U whenever we do a substitution. So it's just the letter chosen to indicate that you're substituting. So you substitute something, and when you do that, it looks quadratic, and then you can solve, and then you basically have to back substitute. So before you even do this, you need to know, is this a problem where I can do that? So I made this little chart. So the first thing is you need to take out the greatest common factor. You always do that first before you decide what method to solve, because that will determine whether you're going to solve by factoring, whether you can solve a quadratic, or if maybe the greatest common factor leaves you with a linear. That's always the first thing that you do. So you want to take out the greatest common factor, and then, so you may have like some number in front and then something like this. If there's a greatest common factor, could be variable in front, but and if there's no quadratic or no greatest common factor, that's fine too. But you're basically looking, is there something with like a variable plus something with something else with a variable, and then the last term is a number. So you're going to look to see, do you have 3 terms, and is the constant, is there a number as one of them, and then you have variables in the 2 terms. If not, then it doesn't even have a chance of basically being quadratic in form, so there's other methods to solve. But if it is fitting that, then we go on to the next part. And so the next part is you let U be the variable part in the middle. So you're going to look at whatever your 3 things are, and you'll have a number and then some variable part plus a number and another variable part and then a number. Whatever the variable part is in the middle is what you're going to set equal to U. And then you're going to square it. And you're going to say, does U squared equal the variable part for the first term? If not, it's not quadratic in form. But if it does equal that, then it's quadratic in form, and we can use this technique to solve. So there's some things that you have to check first to see if you can even use the technique, because not everything can be solved this way. So you have to do some sort of checking to make sure it works. So some examples that are quadratic in form are here. This first one is the easiest to recognize because you have something as a middle term, and then that same thing is squared. So if you did a substitution for x plus 4, you could have 2u squared plus 3u minus 6. So that's the easiest way to see if it's something that is quadratic in form. These other ones are more difficult to see visually. Things that are like the second one here, if they're in this form, you want to say, okay, the exponent on the first term double the exponent on the middle term or the second term. If they are, then it's quadratic in form. So some other examples of something like this would be if you had, I actually went to the highlighter. That's not what I want. But if you had like something to the 8th plus something to the 4th plus a number, that is also quadratic in form. So if you have just single variables with different exponents, you want the first term to be double the exponent on the second term for it to be quadratic in form. And there's other examples of this. Generally, it only works with even exponents because of the fact that you've got a double, so that first exponent has to be even for it to work. Third one is trickier to see because you've got a square root thing. And you could solve that third equation using the techniques of solving a square root equation. So you could solve it that way. But you can also solve it with quadratic in form because the middle is the square root, and then when you square that, you get x. So if you have things in that form, that will work. And then the third type that's quadratic in form, they have fractions as the variables. And the key for those is that the top of the fractions need to match like a quadratic. So it doesn't matter what the denominator is, but the top would have to be a 2, and then the middle would have to be a 1 in order for it to be considered quadratic in form. So these are the 4 basic types that are quadratic in form. There are some where you've got like a fraction inside there, but they're very similar to the first one because you'll have something in parentheses. So you're going to want to, when you see something in one of these, you want to get kind of suspicion and be like, okay, is this something I can solve using this technique? And that's when you want to check. And as you do more of them, you get used to which ones can be used or solved this way. But they're not, I mean, the first 2 are usually the most common that you'll see. The last 2 are very rare. So I wouldn't worry too much about the last 2. It's the first 2 that are very common. And using the steps that I have right here on how to know if it's quadratic in form, that will work for you to check to see if you can use this technique. But these are basically some of what they look like and what to look for. So once you've determined that, yes, it's quadratic in form I can solve, you've basically got 6 big steps, but within these steps you have things to do. So the first is to take that middle term and set it equal to u. And then you square it so that you can find u squared. And you have to do those to check to see if it's in quadratic form already. So you'll already have that done. Then you substitute into the equation u squared and u so that you don't have the complicated thing, you just have those variables. And then that gives you a quadratic that then you can solve, factoring quadratic formula, whatever way you want to solve the quadratic. And once you've solved for u, you then have to substitute in what the original thing looked like. We call this back substitution because you're substituting back in for u what you started with, and then you solve for your actual variable. So you're doing multiple steps for solving. So these are the major steps, and I'm going to go through an example of like the 4 types that I had showed on here. So I'm going to go through an example of each of these so you have an idea of what it looks like. So I'm going to start with the first type where you have things in parentheses here. So here, these are the ones that are easy to see that they're in quadratic in form because you have things in parentheses and something squared and then something not squared. So we start by setting the middle term equal to u. So u is going to be equal to 3x minus 7. And then you need to find u squared. So you need to square both sides. So it's 3x minus 7 squared, which actually is exactly what we have right here. So you don't have to actually do the squaring. You just have to recognize that, okay, that is equal to u squared. You don't have to actually square it. So once you've done that, then you substitute it in. So instead of writing 3x minus 7, that thing squared, I can write u squared. Then I have my minus 6, and then u, because I set u equal to 3x minus 7. And then I have minus 16 equals 0. So once you identify your u and u square, you substitute those in, and now you have a quadratic that is a lot easier to solve than this more complicated looking thing. And I'm going to put boxes around there so you can kind of see what I substitute in. I should actually put the box before the square so you can see that's box squared. So I need to solve these. You've been doing it the hard way. So you've been squaring it out and then going through all of that. It works, but it is very long. It does get you the right answer. But one of the reasons why we teach this technique is because it can save you a lot of time, especially if you're going to take a quiz on this. You don't want to go the long way. You want to do it the easy way. So once I'm in this form and I'm looking at this and I know that this is factorable because I know I'm just looking at it. I've done enough factoring, so I know that this factors to u minus 8 times u plus 2 equal to 0. So the negative 8 times 2 gives me 16. Negative 8 plus 2 gives me negative 6. So now I'm going to solve for u. So I have u minus 8 equal to 0. U plus 2 equal to 0. So u is equal to 8, and u is equal to negative 2. But this is usually where people forget that we're not solving for u, we're solving for x. So we're not done. Once you find u, you need to now plug in for u, x minus 7, because that's what we set u equal to. So instead of u equals 8, we have 3x minus 7 equals 8. And instead of u equals negative 2, we have 3x minus 7 equals negative 2. And so then from here, you're solving for x, because that's ultimately the variable we're interested in. We're interested in x, because that's what's in the original equation. So I'm going to add 7, which gives me 3x equals 15. And then I divide by 3, and so my first answer is x equals 5. And then the second equation, again, I'm adding 7. So that gives me 3x equals 5. And now when I divide by 3, I'm going to get x equals 5/3 as my second answer. And when you want to double check these, you want to double check them in the original equation, because that's where we have x. So you would plug them back into the original to double check that they work. But solving it this way is so much easier than having to FOIL, distribute, simplify, and then factor. So this is why we teach this technique, because it's a huge time saver. And it's really easy to notice in things like this, because it's just set up perfectly to use this technique, because you already have the things in parentheses. So it's easy to recognize what needs to be plugged in where. Okay, you know what? I don't want to do this one yet. Let me do this one. We'll go in order that I have them listed on that other slide. So here we have w to the 4th plus 4w squared minus 45. So first thing is, again, you want to determine u. So we set that middle term equal to u. So u equals w squared. And then you find u squared, w squared squared. Now in this case, we don't see that in the equation, so we need to actually simplify that you multiply the exponents, and that gives you w to the 4th. And so that can be substituted right there. So this would be u squared, and this is u. And this gives us the equation u squared plus 4u minus 45 equals 0. And now you're solving this. This also factors. So I love the ones where they don't have a number in front of the u squared or the squared term, because they usually factor and they're much faster to do. So this will be, let's see, we want a plus 9 and a minus 5. So 9 times negative 5 gives us a negative 45. 9 minus 5 gives us 4. So u plus 9 is equal to 0. U minus 5 equals 0. And we get u is equal to a negative 9, and u is equal to 5. So now that we find u, we need to go back and find w. So instead of u being equal to negative 9, u is w squared. So we have u squared equals negative 9, and w squared equals 5. And these are both quadratic. So I'm going to get 2 solutions from each of these, which will give me a total of 4 answers. And that's what we want, because if you have something that's an exponent of 4, that means you're going to have 4 solutions. 4 solutions. Exponent of 4 equals 4 solutions. So I'm going to get 4 solutions out of here after I take these square roots, because you get a plus and a minus version. So for the w squared equals negative 9, I'm going to take the square root of both sides to solve. So I get w on the left, and then I get a plus or minus square root of negative 9. So this is where the complex numbers comes in that we had to learn about. Square root of a negative means it's going to be an I. That's going to be complex numbers. So I'm going to put the I in front, and then we have the square root of 9. And so then you just take the square root of 9 and you get 3, which usually then I will just write this as we have 3i as an answer and negative 3i as an answer from the first one. Now the second equation, again, we have w squared equals 5. So we're going to take square root of both sides, which gives us w equals plus or minus square root of 5. Now the square root of 5, we can't simplify any further because that's already a prime number. So this gives us 2 answers, square root of 5 and negative square root of 5. So we get 4 solutions here. 3i, negative 3i, square root of 5, and negative square root of 5. And these are not the type of answers you would have been able to find out any other way. This equation can't really be solved except by doing this technique. There's no other way to really do it. When we get, I believe it's week 6, we will learn a different way to solve this, but it's like a guess and check kind of way. So I don't recommend doing that method if you can do this method, because this you don't really have to do any guessing and checking. Are there any questions? Okay. So let me do one with the square root. And all of these are simple ones where they all factor nicely. Sometimes you don't get them to factor nicely and you have to use a quadratic formula, but they do try to give you problems that will factor when you do problems like this, just because it saves some time, because they already can be kind of complicated. So we could solve this by getting the square root by itself, squaring sides, using the techniques of radical equations, but it's much simpler if you recognize it's quadratic in form. So we have the square root of p. So let's say u is equal to the square root of p, because that's the middle term. And then u squared is going to be the square root of p squared. And when you square the square root, those cancel and you're left with p. So that's how we know that this is quadratic in form. So we get u squared minus 8u plus 15 when we do that substitution. So u squared minus 8u plus 15 equals 0. So again, these are designed so that they factor to make our lives easier. Let's see, 3 times 5 is 15. They both have negative to get to a negative 8. So it factors to u minus 3 times u minus 5. So negative 3 times negative 5 is a positive 15. Negative 3 plus negative 5 is negative 8. So I'm going to solve all of these for u, or both of these. So u minus 3 is equal to 0. U minus 5 is equal to 0. I add 3 to both sides to get u equals 3. I add 5 and I get u equals 5. So I solve for u. And you can see why I say factoring is one of the most important things that you guys learn, because you're going to be doing it all the time. So once you get u, now we have to plug it back in. So u is equal to the square root of p. So now we have the square root of p equals 3, and the square root of p equals 5. So this is why we had to learn how to solve square root equations. So we are still solving a square root equation, but this is much easier to solve than it would have been in the original form, because all we're doing is squaring both sides. So that will give you p equals 9 as one solution. And then I square both sides. And we get p equals 25. Now the thing about when you're solving the radicals or the square roots, you always have to check your answer. If there's a single p under the square root, there's likely to be only one solution, and one of these is likely to be an extra solution that pops up from the process of solving, but is not a real solution. We call these extraneous. So since we squared things, we have two solutions here. We do need to double check that there are two solutions, because it's likely there's one. So we need to check them in the original equation. So I'm going to do this on the next slide. We'll start with p equals 9. So our equation was p minus 8 times the square root of p plus 15 equals 0. So I'm going to have 9 minus 8 times the square root of 9 plus 15 equals 0. And I'm just going to go through the order of operations. So first we have to take the square root. Square root of 9 is 3. We're assuming the positive solution because we have no variables here. So if there's no variables, you always assume the positive square root. So that would give me 8 times 3 in the middle, which then we need to multiply. So I'm 9 minus 24 plus 15 equals 0. And now I'm going to just put those in my calculator. 9 minus 24 plus 15 gives me 0. So that works. So I know that p equals 9 is a solution. And we need to also double check p equals 25, because that was the other number that we got. So again, I've got the equation over here on the left, so I'm not going to rewrite it. We have 25 minus 8 times the square root of 25 plus 15 equals 0. So 25 minus 8, and then the square root of 25 is 5. And plus 15 equals 0. 25 minus 40 plus 15 equals 0. Putting that in my calculator, and we get 0. So both answers work. So in this case, we do have two solutions, 9 and 25. So in general, if there's only one thing under the square root, there's one solution, but there can be more, and this is why we have to check, because sometimes there's extras, sometimes they're not. And so we did check, and we found that both of these work, so we do indeed have two solutions to this equation. Are there any questions on this example? Okay, so now we're going to move to the one with the fractions, which I think is probably the hardest of these to solve, just because you have fraction exponents and they're just weird. So we've got 2m to the 2/3 plus 7m to the 1/3 minus 15. So we're going to set equal to the middle, which is m to the 1/3 power. Then u squared is going to be m to the 1/3 squared. And when you multiply exponents, that do m to the 2/3. So that's why when you see something with rational exponents, the tops need to be 2 and 1, but the denominator needs to be the same, but it doesn't matter what the denominator is. So you have to have the same denominator, but the tops need to kind of match there. So now that we've determined what u is, and we can see that u squared is in the equation, you can rewrite it. So I have 2u squared, because m to the 2/3 power is u squared, plus 7u, since we set u as m to the 1/3, minus 15 equals 0. And I believe this does factor. This is going to take a little more thinking on my part. I know that to get 2u squared, you need 2u and u. And because of the 7 in the middle, let's see, I'm trying to think. For 15, we've got 3 and 5. If I did 5 times 2, that's 10. And then the 3, if I subtract it, can get me to 7. So I'm going to make sure that I'm multiplying the 5 by the 2, and then put the 3 in the other spot. And I need to have a positive 10 and a negative 3 in order to get those to add to 7. And then negative 3 times 5 does get me negative 15. So I factored that. So now I have to set each factor equal to 0. So we have 2u minus 3 equals 0. U plus 5 equals 0. So for 2u minus 3 equals 0, I add 3 to both sides, which gives me 2u equals 3. Then I divide both sides by 2, and I get u is equal to 3 halves. And then the second equation, you just need to subtract 5, and you get u equals -5. So I've solved for u. Now I need to back substitute in what u is equal to. So u is m to the 1/3 power. So I have m to the 1/3 is equal to 3 halves, and m to the 1/3 is equal to -5. So people usually don't like solving these types of equations because you have these exponents, and you could rewrite the 1/3 as a cubed root, because that's essentially what it is, and solve it that way. But I think that for most people that looks even more confusing. So what we want to do is cube both sides to get rid of the 1/3, because 1/3 times 3 is 1. So I'm going to just write that in for both of these. So we're cubing both sides. So I get m equals, and then 3 cubed is 27, 2 cubed is 8. So our first answer is m equals 27/8. And then we get m equals -5 cubed is -125. Now, because we raised everything to an exponent, we do have to check our answers. Every time you're solving an equation by squaring, cubing, any of those things, you do need to check. So I'm going to do that on the next slide. Make a little note. Whoops. Check on next. Did not want to erase. Slide. So we've got our original equation, 2m to the 2/3 plus 7m to the 1/3 minus 15 equals 0. And one answer is 27/8. Other answer is -125. And this is where a calculator is going to come in handy, because checking your work here, if you're doing it by hand, can be really, really nasty. So 2 times m, which is 27/8, to the 2/3 power, plus 7 times 27/8 to the 1/3 power minus 15 equals 0. So I'm going to do the exponent stuff in my calculator. My calculator, if you're going to enter in a fraction, you can use the division symbol. I actually have a fraction button on my calculator that I'm going to use. And then when you do the exponent, you need to make sure that you put that 2/3 in parentheses. So like if you were to put this on in your calculator, you also need parentheses around these fraction exponents to make sure it does it correctly. And my calculator gives it as a whole number, or I mean as a mixed number, which is just the way that my calculator does it. But I can convert those to improper fractions. So I did the whole 2 times that exponent thing here. So this whole thing in my calculator gives me 9 halves. And now I'm going to put this whole thing on the calculator. And this is where it's really important to enter it in correctly. Using the Desmos scientific calculator is actually a good method here. Let's see, and this gives me 21/2 minus 15 equals 0. And again, I'm going to just use my calculator and work with these fractions to see what I get. And these do give me 0 equals 0. So this nasty looking fraction does work. Now what I'm going to do is to do the second one. Oops, hit my keyboard. I'm going to open up Desmos. I can get it to open up, and I'm going to use the Desmos scientific calculator to enter it in. So we don't want the graphing calculator, we want the scientific calculator here. So before I use Desmos, I'm going to write out what it is that I'm actually entering in. So we're doing 2 times negative 125 to the 2/3 plus 7 times negative 125 to the 1/3 minus 15 equals 0. So we want to do the left side to simplify that, and we'll use the Desmos calculator for that. So I can type my 2, and then I'm going to put in my parentheses negative 125, close the parenthesis, and then now we need to do this fraction thing. So you're going to hit the fraction button here, the A to the B. That puts me in the fraction, and then I want to actually have or I keep saying fraction, puts me in the exponent. This is the exponent button, puts me up there. Then I want to have a fraction up there. So I hit that, and we're doing 2/3. And then I have to hit my side arrow to get out of there. And it's the same thing you would have to do in Alex if you're doing exponents and stuff. You have to keep hitting the arrow to get out. Plus 7 times negative 125. I'm going to hit my fraction button, the exponent button, and then hit the fraction button. Here we've got it down 1/3, and then minus 15. And you can see that then that also comes to 0. So that means that this does work. It is a valid solution. So when we plug it in, this also gives us 0 equals 0. So we have negative 125 as a solution. So using the Desmos calculator is great for checking your work, especially when you have complicated things like this. And what's really nice is that if I wanted to go back and check the other one, all I have to do is just edit it. So I put in here, I put in my fraction, 27/8. Fraction 27/8. And you don't have to go and retype the whole thing. It's actually almost easier than using a hand calculator, because on a hand calculator, you basically have to type the whole thing. Here, I can just copy and paste. I can delete, I feel like it's more powerful. So that can also double check. And then if I wanted to just do like the left part there, that gives me 4.5, but you hit this button and that converts it to a fraction, and you can see that you get the 9/2 that I wrote down. So this is how you solve equations that are quadratic in form, and now you've seen how to solve the 4 major types. And you can see that there's different types of steps for solving once you plug it in. Like this one, we had to cube each side. Here, we're just solving a linear equation. We had to solve a square root equation here, so we had to square both sides. And here, oops, that's the same one. I meant to click below it. Here, we ended up having to take the square root of both sides. So you can see that once you get to the part where you plug it back in, what I have in blue here, the technique changes based off of what type of equation you have. But in the orange is the same thing. You're just solving a quadratic every time when you do that substitution. But this is why it's really important that we learn all these different types of solving, because you can see on the right side that depended on your equation, what you ended up with. And you have to know, oh, I got a quadratic, this is how I solve. Or I have something with a radical, this is how I solve. So it's really important that you recognize the types of equations that you have so that you know how you solve it once you get it back, once you back substitute. I had a conversation with someone earlier And so I just wanted to point out, I'm in the Vital Source version of the textbook, but these are also in the Alex version of the textbook. But there's these things called problem recognition exercises, and these are good for you to recognize. Do I have a quadratic? Do I have a linear? So these are really great just to help you. If you're one of those people that struggles with, I see this and I don't know what to do, I would go into the textbook and do these problem recognition exercises for extra practice. Like there's some for every chapter. So here there's some for operations and arrays. And so it's just practicing simplifying so you know what step to do when. In chapter 2, there's problem recognition exercise operations on exponential. So these things are really cool. I think they're really great to help you study if that's where you struggle with. You struggle with, I don't know what I need to do. So, or like I can't tell if it's an equation or an expression. This can help you if it ever loads. You can do these, and all the answers are in the back of the book. I think in the Alex version of the textbook, the answers are right there, and you can like click a button or something. So I actually prefer using the Alex version of the textbook because here this also doesn't have any of the videos embedded or anything like that. So this is not as easy to use. But these things are really great. They're present. And if that's where you struggle, especially if you like struggle with going on a quiz and be like, I don't know what step to do, doing these can really help you out. So do you guys have any questions for me? I will take that as a no. I'm glad that you came too. I'm glad that not only did you come, there was 2 people. Jamal came later, so that was good. So because I am going to try to get this out today, I'm going to have to wait for the recording to process and all that, and I'm probably going to just do maybe some quick edits or whatever. I usually check the sound and things like that, but I will get it out emailed today, so that way you can review it again if you want, use it as a reference. I'll make sure to post the PowerPoint and all that. So glad that you came, glad that this was helpful, and I'll let you know when I'm going to do the one for next week and what it will be on.